Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about the properties of the diagonalization. What does it implies for us, those properties, and how we can use them. So diagonalization in one type of the factorization of the matrix, when we are going to represent a matrix, a square matrix with the n rows and n columns, with n distinct eigenvalues in the following form. Essentially, it's going to be written as the multiplication of the matrix X, which is going to contain the eigenvectors of this matrix A as the columns, and the lambda, which is going to have the eigenvalues of this matrix A as the diagonal entry. So the lambda is going to be the diagonal matrix, and we have to additionally multiply this as X inverse in order to get the A. So let's try to understand, so what is the x, lambda, and x inverse, and how this multiplication is going to give us the A in the following example. So in our previous video, we found the eigenvalues and eigenvectors of this following matrix. So the A is going to have two eigenvalues, so 5 and 3 essentially. And the eigenvector, which is going to correspond to the 5, is equal to the x1 and 1. And the eigenvector which corresponds to the 3 is going to be simply minus 1 and 1. The inverse of this matrix X can be found using the formula to find the inverse of the 2 by 2 matrix, and this is going to be the following matrix. So I would like to now multiply the three matrices in order to get the A. So let's multiply first of all the X to the lambda. So this is 1, 1, minus 1, and 1 multiplied to the 5, 0, 0, 3. When we multiply the diagonal matrix from the right, so it's going to be just multiplied to the corresponding columns of this matrix on the left. So this is going to be equal to 5, 5, minus 3, and 3. So now we are going to multiply this to the x inverse. So in this case, it's going to be 1 minus 1, 1, and 1. So I would like to say there are different type of the multiplication of the two matrices. I would like to multiply now these two matrices as a linear combination of the columns of the first matrix. So in this case, what I get is I will get this column. So and I'm going to use the entries of this column as the coefficient of the linear combination. So essentially, the first column is going to be multiplied as 1, and the second column is going to be multiplied as a minus 1 as the entries of this column. So what does it mean? It means I just need to subtract the second column from the first one. So the 1 and 2 stands here. So if you subtract the second column from the first one, you're going to get 8 and 2. So at the same time, I'm going to use the entries of the second column here as the coefficient of the second linear combination, where I'm going to multiply the first column to the 1 and the second column to the 1. It essentially means that I just need to add these two columns. So essentially, if you add these two columns, what we get is 2 and 8. Well, if you multiply all of the entries of this matrix to the 1 over 2, you're going to get exactly the A matrix. So now what we want is, once I understand that, hey, it is possible to decompose the matrix to the multiplication of the three others, how I can use this. So why actually I need to make so much efforts in order to bring the matrix into the three other matrices. So what we gain from that. So well, it appears when we power up the matrix, its eigenvalues and eigenvectors are going to change or are not going to change. So we can use the stack in order to power up the matrices. So essentially, the eigenvectors of the powers of the A are not going to change at all. And eigenvalues of the matrix A, when we power up the matrix A, are going to change. And we know exactly how they are going to change. So we can easily find the eigenvalues and eigenvectors of the powers of the A matrix. Well, the explanation for this is in the followings. So let's assume that, hey, this is going to be the x1 is the eigenvector of the matrix A, which is going to correspond to the following eigenvalue, lambda 1. Well, I'm going to multiply the x. So what does it mean that the x1 is the corresponding eigenvector of the matrix a. It means that if you multiply a to the x1, you're going to get lambda 1 times the x1. So this is what does it mean that the x1 is the eigenvector and the lambda 1 is the eigenvalue. Well, I'm going to just get this x1 and I'm going to multiply this to the a in the square. So I'm not going to just multiply the x1 to the a square. What I'm going to do is I'm going to expand this a in the square a little bit. So I'm going to rewrite this a in the square as a times the a times the x1. So you see, so I can multiply the first two the matrices first of all. So if you multiply this, you're going to obviously get this one. So now I can just substitute this to here. So what I get is essentially a times the z lambda 1 x1. So since the lambda 1 is the constant, we can write this down as a lambda 1, a to the x1. And again, I've got this a to the x1, and I'm going to substitute this a to the x1 again with the lambda 1 x1, which is going to be simply lambda 1 in the square times the x1. So if you look to the first term and the last term of this equation, what we get is a in the square times the x1 is equal to the lambda 1 in the square times the x1, which is structurally very much similar to this equation, right? So you're multiplying a vector to the matrix and you're getting a same vector, which is just scaled with some constant, and this constant is lambda 1 in the square. So what does it mean? It means that so this vector x1 is the eigenvector of the a in the square. So it appears if you square the a, you're going to get the same eigenvector. And well, eigenvalues, it appears, are going to change, but we know how they're going to change. So they are going to be simply squared of the eigenvalues of the a. So what I want is I would like to check this out for this matrix. So I'm going to square this matrix A and I'm going to find its eigenvalues and eigenvectors. So let's first of all square this matrix A. So in order to do this, we just need to simply multiply the matrix A to itself. So it's going to be 4, 1, 1, 4 times the 4, 1, 1, 4. Well, if you multiply this, it's going to be the first row to the first column. It's 16 plus 1, 17. So the first row to the second column is going to be 4 plus 4, it's 8. Then the second row to the first column is going to be 8 again. And the second row to the second column is going to be 17. Well, first of all, I would like to find its eigenvalues. In order to do that, I'm going to use the property that the sum of the eigenvalues should be equal to the trace of this matrix, and the trace of this matrix is equal to the 34. And the multiplication of the eigenvalues should be equal to the determinant of this matrix, which is simply 17 in the square minus 8 in the square, which can be written as a 17 minus 8 times as a 17 plus 8. So well, the 17 minus 8 is equal to the 9, and 17 plus 8 is equal to the 25. You see, so these two numbers are just the squares of these two numbers. So, well, the eigenvalues of the square of the a are going to be simply the squares of the eigenvalues of the a. Well, now I would like to show that the eigenvectors of this matrix are going to be the same as the eigenvectors of the a. Well, now let's find the eigenvectors of this matrix A in the square. In order to do that, we need to create the matrix A in the square minus lambda 1 times its identity, and we have to find its spatial solution. So what we do is, so we first of all need to subtract this. So essentially 17, 8, 8, 17. And we're going to subtract the eigenvalue, the first eigenvalue, which is going to be 25. So let's say 25, 0, 0, 25. So 25 times this identity. So what we get is essentially, so we just need to subtract the 25 from the diagonal entries of this matrix, which is going to be minus 8, 8, 8, and minus 8. Right? So well, let me copy this to here. Say minus 8, 8, 8, minus 8. So we need to figure out the vector x, so that if I multiply this to this, I need to get the 0 and 0. And I'm going to try to figure out what this vector is. So you see, so the two columns of this matrix are very much similar, right? So this column and this column here. So they are just opposite vectors, right? So what I can do in order to get the 0 vector, I can just add them. So essentially, I can put the 1 and 1 to here so that this becomes 0. So that's going to be the first eigenvector of this matrix A in the square. So at the same time, if you subtract the A in the square minus lambda 2I, it is going to be equal to 17, 8, 8, 17 minus 9009. So essentially, if you subtract the 9 from the diagonal entries of this matrix, we get 8, 8, 8, 8. Well, what vector is going to make this to be equal to the 0 and 0? So essentially, which constant you have to multiply the first column, and which constant you have to multiply to the second column, and if you add them, you're going to get 0 and 0. So since both of these columns are the same, you just need to subtract the first column, for example, to the minus 1, and the second to the 1, right? Just subtract the first column from the second. If you multiply the first column to the minus 1 and the second column to the 1 and add them, you're going to get exactly 0 and 0. So essentially, the second eigenvector is going to be minus 1 and 1. Well, if you look at the eigenvectors of the A, so here are the eigenvectors of the A matrix, they are the same. So it was like a 1 and 1 minus 1 and 1. So you see, if you power up the matrix A, the eigenvectors are not going to change. Eigenvalues are going to change, but we know how they're going to change. So they are going to be squared or cubed, or so they're going to be powered up to the same power as the matrix A. So well, what does it implies for us is that, so hey, if you are given the matrix A, which can be diagonalized, so essentially which can be expanded or decomposed as a multiplication of the three matrices, then the power, k's power of this matrix A can be found in the following way. So I'm going to write down, so hey, so if you are given the matrix A and its decomposition, I would like to find the k's power, so where k can be any number, for example, 100, 1,000, or any other number. So it is going to be equal. So let's try to do this with the smaller number. So let's try to do this with the 3, so that it will be easier for us to understand what's going on here. So I'm going to rewrite this in this way: a times the a times the a. Okay, so I'm going to substitute every appearance of the A with its decomposition. It's going to be x times to the lambda x inverse for the first A, x times to the lambda to the x inverse for the second A, and x times to the lambda x inverse for the third A. So I'm just substituting the A. So if you open all the brackets, what you get is x lambda x inverse, x lambda x inverse, x lambda x inverse. Well, if you multiply these two matrices, it is going to be the identity. These two matrices is the identity as well. And what you get is x lambda 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 x inverse, or it can be written as the x lambda in the cube x inverse. Well, since the lambda is a diagonal matrix, it is going to be very much easily found. So we can find its powers very easily. So essentially, if you are given some diagonal matrix, lambda 1 and so on, lambda n, its cube, for example, is going to be simply the cubes of those entries, the constants. Okay? So it essentially tells us that, hey, a cube is going to be very much similar as the A, as the decomposition of A. So we can multiply the x to the lambda cube and x inverse in order to find a cube or any other power. So in general, the k's power of the matrix A can be found by multiplying the x to the lambda in the power of k times the x inverse. So let's do an example. So let's find the k's power of this matrix. So in order to do this, I'm going to find, first of all, the eigenvalues and eigenvectors of this matrix, find the inverse of the eigenvector matrix, and so on. So in order to find it, so since this is the triangular matrix, so for any triangular matrix, the eigenvalues are going to be on the diagonal. So essentially, the first eigenvalue is going to be 1, and the second eigenvalue is going to be 3, so simply the diagonal entries of this matrix. So it comes from the essentially the property that the sum is going to be equal to the trace. So sum is equal to the 4, and the determinant is equal, so the multiplication of the eigenvalues is equal to the determinant, which is equal to the 3, right? So which fits to this. So the multiplication is 3, and the sum is equal to the 4. So let's find the first eigenvalue vector. So in order to do this, we need to subtract the lambda 1I. So essentially 1 should be subtracted from the diagonal entries of this matrix. If we subtract, what we get is 0, 2, 0, 2. Right? So if you so you see the second column is the pivot column. So this is already in the so this might be brought to the row echelon form by just multiplying the first row to the -1 and add this to the second row. So let me write this. So the first row should be multiplied to the -1 and added to the second. And what we get is 0, 2, 0, 0. So the second column is going to be the pivot column, and the first column is the free. So that's why the x1. So we need to find a special solution of this matrix, right? So x1 is going to be equal to the 1. If you substitute this to there, it's going to be 0 times the x1 plus 2 times the x2 is equal to the 0, which means that x2 is equal to the 0. So that's going to be the first eigenvector. So the first eigenvector is going to be simply 1 and 0. Okay, so that's going to be the eigenvector, which is going to correspond to the 1. So we are going to now find the second eigenvector by just subtracting the 3 from the diagonal entries of this matrix. A minus lambda 2I is going to be -2, 2, 0, 0. Okay, so you see, so these two columns are similar. So this column is very much similar to this one. So if you want, you can again, so the second column is the free, so it's a free column. So that's why x2 to be equal to the 1. So the free variable is going to be equal to the 1. And if you substitute this to here, it's going to be -2 times the x1 plus 2 times the x2 is equal to the 0. And if you find x1 from here, it's going to be simply equal to the 1. Right? So the second eigenvector is going to be 1 and 1. So this is going to be the second eigenvector. So I found the two eigenvectors, and I'm going to put them to a matrix. If you combine all of these matrices, what we get is the following matrices. Well, I think there was a mistake. So the eigenvalue matrix here is wrong. So it should be 1 and 3. Okay, so we just found that the first eigenvector is equal to the 1 and 0, and the second eigenvector is going to be 1 and 1. The inverse of this matrix X is going to be the following matrix, right? So it is very much easily found. So using the formula, so if you remember, the inverse is going to be 1 over determinant of the anyway. So if you are given the matrix A, B, C, D. Its inverse is going to be 1 divided to the AD minus BC times to the AD, or DA, sorry. So DA, D and A, minus B minus C. So just using this formula, you can find the inverse of this matrix here. Well, what we need to show now is we would like to find the k's power of this matrix A. So the A in the power of k is going to be equal to, so 1, 0, 1, 1, times to the k's power of the lambda. So it's going to be simply 1 in the power of k, 0, 0, 3 in the power of k, times to this matrix 1, 0, minus 1, and 1. Okay? So let's do this. So let's multiply the first two matrices again. So I'm going to multiply this entry to the first column, and the second entry is going to be multiplied to the second column. And what we get is 1, and so simply 1, because 1 in the power of k is 1. So 1, 0, so 3 in the power of k, 3 in the power of k. So we have to multiply this now to the second matrix, 1, 0, minus 1, and 1. And again, you can do multiplication of these two matrices in a very much different ways, and I'm going to do this by combining the columns of this matrix using the entries from here. So 1, 0 means multiply the first column to the 1 and the second column to the 0. It is going to be simply 1 and 0. And here, minus 1 and 1 means multiply the first column to the minus 1 and the second column to the 1. Or subtract this first column from the second. So this is going to be 3 in the power of k minus 1 and 3 in the power of k. So that's going to be a in the power of k. So if you would like to find, for example, a in the square, just substitute the 2 instead of k and the all the appearances of the k on the left hand side, and that's going to be the a in the square. So essentially, if you okay, so if you would like to find a hundredths power of the a, just substitute the 100 instead of k, and that's going to be the hundredths power of the a. So in our next video lectures, we are going to discuss how this idea of finding the any power of the a can be applied and the real world applications of the matrices. So far, that's about the powers of the matrices. So I hope that this video was helpful for you.